CS 3351 Digital Principles and Computer Organization. Topic is Pipelining Hazard, presented by Devi Visalakshi, Assistant Professor of CSC Department, Rohini College of Engineering and Technology. Pipelining hazard. There are situations in pipelining when this next instruction cannot execute in the following clock cycle. These events are called hazards. Hazards are there three different types: structural hazard, data hazards, and control hazards. Structural hazard. Structural hazard occurs when a planned instruction cannot execute in the proper clock cycle because the hardware does not support the combination of instructions that was set to execute. A structural hazard in the laundry room would occur if we use a washer dryer combination instead of a separate washer and dryer, or if our roommate was busy doing something else and would not put clothes away. Our carefully scheduled pipeline plans would then be foiled. Data hazards. It is also called a pipeline data hazard when a planned instruction cannot execute in the proper clock cycle because data that is needed to execute the instruction is not yet available. Data hazards occur when the pipeline must be stalled because one step must wait for another to complete. Control hazards. It is also called as branch hazard when the proper instruction cannot execute in the proper pipeline clock cycle because the instruction that was fetched is not the one that is needed. That is, the flow of instruction addresses is not what the pipeline expected. A control hazard arising from the need to make a decision based on the results of one instruction while others are executing. Branch prediction. A method of resolving a branch hazard that assumes a given outcome for the branch and proceeds from that assumption rather than waiting to ascertain the actual outcome. Static branch prediction. A more sophisticated version of branch prediction would have some branches predicted as taken and some as untaken. In the case of programming at the bottom of loops or branches that jump back to the top of the loop, since they are likely to be taken and they branch backward, we could always predict taken for branches that jump to an earlier address. Dynamic branch prediction. Dynamic hardware predictors, in stark contrast, make their guesses depending on the behavior of each branch and make change predictions for a branch over the life of a program. Following our analogy in dynamic prediction, a person would look at how dirty the uniform was and guess at the formula, adjusting the next prediction depending on the success of recent guesses. One popular approach to dynamic prediction of branches is keeping a history for each branch as taken or untaken and then using the recent past behavior to predict the future. Pipeline data bar. The division of an instruction into 5 stages means 5-stage pipelining, which is turn means that 5 instructions will be executing a single clock cycle. So that instructions are instruction fetch, instruction decoded and register, file read, execution, data memory access, write back. These are the 5 steps was filled in the pipeline data bath. So this is the structure of single cycle data bath. Here instruction fetch, instruction decode, register fetch, execute address calculation, memory access, as well as write back. For each and every sections are there. Pipeline control. Adding control to the pipeline data path is referred to as pipeline control. It is started with a simple design that views the program through pipeline bars in between the stages. The first step is to label the control lines on the existing data path. To specify control for the pipeline, we need only set the control value during each pipeline stage because each control line is associated with a component active in only a single pipeline stage. We can divide the control lines into 5 groups according to the pipeline stage. Instruction fetch. The control signals to read instruction memory and to write the PC are always asserted, so there is nothing special to control in this pipeline stage. Second one is the instruction decode. As the previous stage, the same thing happens at every clock cycle, so there is no optional control lines to set. And third one is the execution or address calculation. The signals to be set or registered DST, ALU, OP and ALU SRC. The signals select the result register, the ALU operation and either read data to or signed extended immediate for the ALU. Fourth one is the memory access. The control lines set in this stage or branch memread and memwrite. The branch equal load and store instructions set these signals respectively. Recall that PCSRC selects the next sequential address unless control asserts branch and the ALU result was 0. Fifth one is write back. The two control lines are memory to register, which decides between sending the ALU result or the memory value to the register file, and register write, which writes the chosen value. Since pipelining the data path leaves the meaning of the control lines unchanged, we can use the same control values.